All right, let's start on antidifferentiation by guess and check, which is basically knowing what you have learned from the differentiation standpoint, working backwards to take a velocity function and move it to a position function, or even an acceleration function and move it to a velocity function. So what is an antiderivative of the horizontal line f of x equals 0? Well, basically any function that has a slope of 0 is also a constant function. So that means what it's saying here is a function whose derivative is 0 everywhere must have a horizontal tangent line at every point on the graph, so that only happens if the function itself is a constant. So if the derivative of a function equals 0, then the function must equal some constant c on that interval. And so we use a capital C in calculus to represent that constant. So the most general antiderivative of some function, little f, we typically say that little f represents the derivative function, whereas big F represents its antiderivative. So that would be effectively that the derivative of f, big F, is equal to little f. So little f is going to have a family of antiderivatives in the form of big F of x plus c, where c is just a constant. And the reason why this creates a family of functions is that this plus c creates a vertical shift. And so there is a family of functions, big F, that all have the same general shape, but that are shifted anywhere up and down on the coordinate plane. Think about it. If you have a function that is moved up or down, it doesn't change the slope of the function at any x value. All it does is change the y value of the function. And so a family of functions, think about a basic parabola. Y equals x squared, y equals x squared plus 1, y equals x squared minus 3. All of those functions will have the exact same slope where x equals 0. In that case, the slope is a horizontal tangent line. So the vertical shift does not change the derivative of a function, and so we call this big F of x plus c a family of functions all with the same derivative. So this is saying if big F and big G are both antiderivatives of f, then they must just differ by some constant. That means that G is just some vertical shift from x. So you're just adding a constant to G to equal f. So let's do some examples here. First of all, we're given functions. We're given little f equals 5. So when I antidifferentiate for this one, think about it. What function has a slope of 5 everywhere? Well, big F, and you have to write big F equals because these are functions, they require equations. Big F is going to equal 5x. And so 5x always differentiates to 5 because it's a line with a slope of 5. Now they're asking us to get the general antiderivative, so we have to include a plus c because there are going to be many lines with a slope of 5 that are all vertical shifts of each other, and all of these functions with slopes of 5 have a derivative that equals 5. So basically what we're doing here is we are undoing the power rule. And so notice that 5 is just 5x to the 0. And what I did was I took 5x to the 0, I went up a degree to get to 5x to the 1, and actually I divided by my new degree. I divided by 1, and that gave me the function 5x plus c when I simplified. So we're going to continue to undo the power rule here. Big F of x equals, this is a derivative, which is equal to 5x. That has a degree of 1. So to undo the power rule, we are going to go up a degree to 2 and divide by the new degree and add a plus c. Let's do it again for the third problem. We take our degree of 2, we add a degree, and we divide by the new degree, and I'm writing that as 1/3, and of course we add a plus c. So I'm going to pause, or I'd like you to pause, excuse me, and I'd like you to try the rest of the problems on this page, and then come back and check your answers. Okay, let's take a look at these answers. We are going to continue for number 4 with undoing the power rule. So we go up a degree from t squared to t cubed over 3. Notice we divided by the new degree. T went to t squared over 2, and we added a plus c. For number 5, this is not a power rule. But you do know the function that differentiates to cosine, and that function is sine. Sine differentiates to cosine, and therefore the antiderivative of cosine is positive sine, and of course plus c for the general antiderivative. For number 6, we are applying the power rule. It might be easier for you to write this as the square root of z, to write it as z to the 1/2, because then you can go up a degree to 3/2, and then when you divide by 3/2, it's the same as multiplying by its reciprocal 2/3, and then you add a plus c. Next few problems. This is an interesting one. Little h of z equals 1 over z. Well, think about it. What function do you know that differentiates to 1 over z? That's the natural log function. Well, if you notice here, we wrote that big H of z equals the natural log of the absolute value of z plus c. Why is that absolute value there? Well, this function 1 over z graphs in both the first quadrant and the third quadrant. But when I take the natural log, I can't take the natural log of a negative number, so I have to do something to remove the third quadrant values from the domain of 1 over z. That's why we put in the absolute value. Keep that in mind when you're doing your gateway and when you are taking an AP exam. If you do not have the absolute value around your z there, you will be marked incorrect. For the next problem, number 8, once again, this is reversing the power rule. It might be easiest for you to write 1 over t squared as t to the negative 2. Then we add a degree to get to negative 1 and divide by negative 1. And notice that we left this here as negative t to the negative 1. That's totally fine. We could have also written this as negative 1 over t plus c. That's totally fine. We don't care how you leave a free response problem. It does not matter whether you leave a positive or a negative exponent. When it does matter is when you're doing a multiple choice problem and you have to match to their solution. So beware that in multiple choice you would have to do some matching. 1 over z cubed is the same thing as z to the negative 3. So we go up a degree to negative 2 and we divide by negative 2 and we add the plus c. So I just want to point out here that when we had a fractional exponent, we used the power rule. When we had an exponent in the denominator, i.e. a negative exponent, we use the power rule, except in this case where the exponent in the denominator was 1. When you have that, that is the only time that you integrate to the natural log of the absolute value of the expression in your denominator. It has to be a linear component in the denominator. Okay, what function differentiates to e to the z? E to the z does. So e to the z integrates or antidifferentiates to itself plus c, don't forget your big F of z. Sine integrates to negative cosine because you need a negative cosine to differentiate to sine. So people get confused with the negatives sometimes when they're integrating and differentiating between sine and cosine. So I always recommend that you think to yourself, let me make sure that this works. That's the whole check part of guess and check. When you integrate this sine, if you tried to go just to cosine, you would have realized that cosine differentiates to negative sine, so you do need a negative here to counteract that. And then we have a nice power rule problem here where on each component, we're going up a degree and then we're dividing by our new degree.